right. OBS is streaming, but you are not seeing anything on the screen. Because I haven't connected the projector to the computer. Minor steps, just. There we go. So that should pop up. There we go. All right, excellent. All right, so it's already recording. Just want to kind of confirm that before we move on. Okay, I'm gonna close some of these screens and get back to this particular class. Alrighty. This is Monday, Wednesday class. Okay, I can't really give you the solution of the positive or negative exponent homework yet, because one person, was sick due to sickness, got extra time, so I can't really, give you, the answer yet. But when that particular deadline has passed, then I'll give you guys the solution. So for the time being, you just kind of have to bear with me, and then we'll move on to continue our topic with memory devices. And we already talked about D flip-flops the other day, okay? So let me get to the section that we are on. Okay. This is the stuff from my cisp310 class. Let me check. All right, so maybe I don't have a tab on already, so we'll just go ahead and start one. There we go. All right. So I think, because I watched the video from the previous class, just earlier this morning, and it was already displaying this screen. So did we talk about this whole thing, what a register is? We did? No? Briefly. Okay, very good. So we'll start with this one, okay? What we can see is we have a whole bunch of these individual items. And do you guys still remember what each one is representing? Each one is representing the previous concept, which is this slide here. So let's just take a look at this picture first and try to identify what it is. It has one single output, which is just a bit. In other words, it is a memory device for 1 bit, okay? We have the usual stuff, okay? We have the data, okay? And from the first D flip-flop that we talked about, which is level sensitive D flip-flop, we know what enable is supposed to do. When enable is 1, the device, pays attention. When enable is 0, it does not pay attention. But the second device, or the second D flip-flop device that we talked about, which is an edge-sensitive D flip-flop, also, has a clock, which basically means, we only capture the data, when there's a rising edge on the clock pin. When the clock pin goes from 0 to 1, at that particular instant of time, we capture whatever is on the data pin, and remember, that as the memory of this particular item. So there's only one other item that is added in addition to being level sensitive and also level sensitive. It's the reset pin. The reset pin, along with O1, an OR gate, and A3, which is an AND gate, serves only one purpose, okay? When the reset pin goes from 1 to 0, this is an active low pin. When reset is 0, what it is going to do is it's going to force A3 to be a 0. When A3 outputs a 0, it goes into the R pin of the SRC SR latch, which will cause the SR latch to reset, which will also cause the output or the Q to become 0. So reset itself, doesn't care about any one of the other pins. Your data can be whatever, your clock can be whatever, your AEN can be whatever. When reset goes from 1 to 0, the device resets to 0. Is that okay? So what we have here, in a very long name, is a gated edge-sensitive, and resettable D flip-flop. Pretty long name, okay, because it has all of those attributes. So are we okay with this picture? All right, okay. So the next one is basically saying, okay, if we package this into its own chip, okay, which becomes these little items here, let's see what this particular circuit is going to do. The first thing we want to do is to look at this and go like, okay, it looks really complicated, but it's not. It is not as complicated as it seems. Because when you look at the reset line, okay, how does it connect to each individual device inside? So you track down the reset line. Okay, there's a tap here, there's a tap here, a tap here, tap, 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 tap. In other words, all of these devices, all of these resettable, edge-sensitive, and gated D flip-flops, they're all connected to the same reset line. Is that okay? What about the clock line? What do you think? Same thing. The clock line, the clock pin is connected to the clock of every single one of these. All right? So you can track it down. The clock line here, it taps into here, which is the clock, taps into here, which is the clock, taps into here, the clock, 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 and clock. Okay? So this topology is also known as multi-drop. It's called a multi-drop topology, where one pin that is driving connects to a whole bunch of pins that are receiving. It's called a multi-drop topology. Okay, there's one more, which is EN. So what can you tell me about EN? It's the same thing. It multi-drops into every single smaller device in this entire circuit. So the only thing that is not multi-drop is the data pin. The data pin is an 8-bit pin, and I use a splitter to split out all 8 individual bits. And each individual bit now goes to a different D flip-flop. Like bit 0 only goes into the device at the top. Bit 1 goes to the second device, bit 2 goes to the third device, and so on. So the data pin is the only thing that is not multi-dropped. When you look at the output, the Q pin of each individual device, they all merge using a splitter back into the output pin, which is also 8-bit wide. So what this is just a multi-bit D flip-flop if you want to look at it that way. So from now on, instead of calling this a multi-bit gated, resettable, and edge-sensitive D flip-flop, can we just call this a register? Okay, so we'll just call this a register from here on. Is that okay? Yep,
So
go ahead.
The reason why we have like physical devices like hard drives is because we have to, because once the power goes out, all this data is lost, so we need to pair this
Correct.
to something physical.
Yes, so in order for something like this, okay, so let's go all the way back to a SR latch, because this entire slide starts with a very simple memory device, which is our SR latch. So I'm just scrolling all the way back to SR latch. Oh, okay, we don't have the picture for that. But the thing about the SR latch is when it powers up, we don't even know what the state is. And that's why Logisim complains about it when we put an SR latch into a circuit. The outputs are red in color because we don't know what state it's supposed to be in. And that's why it needs to be resettable so that when you power up a computer, a reset line that is global to the entire motherboard will tell every single component and say, okay, you and you and you and you, everybody, reset to whatever the reset state is supposed to be. Now, normally we say the reset state is 0, but that may not be the case for certain devices. So for certain devices, the reset state may be a 1. Okay, that's okay too, as long as it is deterministic and we know that it is safe for that device. It's okay. Doesn't have to be 0. So does that answer your question?
Yeah.
Okay.
Another question. What's the most basic way you can save the value you got when you added the register? So when you reset,
Okay.
what's the most basic physical thing you can do to save that value?
There are, okay, so you're talking about a non-volatile storage, compared to what we have talked about up to this point. They're all volatile. So non-volatile in a more traditional sense, back in the really old days, you punch holes on a piece of paper. I mean, you literally do that. Okay, so what you do is you have a device that scans through memory locations, and if the location in memory is, let's just say, 1000, 0011. Okay, so I'll just write it on the board so we can kind of track that. It's not important from the discussion here, so I will just kind of write it down on the board. It's not on the projector. So, to remember this particular bath pattern, on a punch card, you will just have, positions where, I don't know whether they put a hole, where there's a 1 or 0, but it's one or the other, right? So let's just say that, it is with the ones positions that have a hole. So now on a punch card, this is how it remembers the content of 10000011.
Oh, that's awesome.
Yeah, punch cards. Those are punch cards. And if you look at, and then later on, people use audio tapes, like cassette tapes. I know many of you do not grow up with cassette tapes, but ask your parents, okay? Your parents will know what a cassette tape is. So there are old, personal computers like the Apple II computers that would use an audio tape, like an audio cassette tape, to kind of encode memory content. So basically what it does is it scans through the memory content, and then depending on whether it's a 1 or a 0, it would emit a different tone. Okay, so a high tone can be a 1, and then a low tone can be a 0. Okay, they may use different types of modulation, frequency modulation or amplitude modulation or mixture of the two, but nonetheless, it is translating, the zeros and ones into physical quantities that can be stored in a persistent way, kind of persistent.
Awesome.
Yep.
Okay, cool.
Yep. So your hard drive today is a much more modern and super high performance version of all of that stuff. It uses the polarity of magnetic field. So if it's north, if north is pointing this way, it is a 1. If north is pointing this way, it's a 0. So that's how zeros and ones are stored on a hard drive. But I mean, if I continue to teach this class for 5 more years, people will be asking me, what is a hard drive? Because every computer will have a solid state drive instead of a hard drive. So a solid state drive is based on flash technology. Now, I haven't really looked into flash technology that much. The only thing I can remember was there's a quote unquote well, a concept of a well, which can store electrical charge. And that's how it can maintain the state of a 0 or 1, even after you power off the device. But I'm not 100% sure. I'm not familiar with flash technology to explain how it works. Yep.
So on a disk, though, I mean, is there a small quantized space that you can magnetize a certain way?
So that depends on how fast the platter is spinning, and also how fast the disk head can change its polarity, or pick up a change of polarity. So it can only go so fast. In other words, your spinning speed on a regular desktop hard drive is 7,200 RPM. On a laptop computer, it's typically 5,400 RPM. It's a little slower to save energy. IBM had and other manufacturers now have experimented with 10K, 10,000 RPM hard drives. So they are faster because when the disk spins faster, they can pick up the zeros and ones faster too. But how fast your magnetic head can change the polarity of a small area on the platter and how fast it can pick it up, there's a certain limit of how fast that can be done.
Yeah.
So the density you can store on a single track is limited by the media physical limitations. Because in order to change the magnetic field of a certain area on the platter, it takes time. So that time is kind of your real limitation of how fast you can store or retrieve data from a hard drive.
But how does the actual changing of a little piece of the metal plate? How does that actually happen?
It's the same technology as a cassette tape, so and also a floppy disk. Yeah. So basically, you have a material that is it called ferrite? Ferrite. It's based on iron,
Yes.
okay, and as a result, it would react to an external magnetic field and change its magnetic field accordingly to align to the external magnetic field.
Okay, so you can do that atom by atom almost?
It's probably, let's see, that I do not know. Yeah, I don't know exactly how magnetism works, like how the polarity of something changes how the material changes its polarity based on the external field. That part I do not understand.
Right, yeah, right.
Yep.
Okay. Thanks.
Oh, it doesn't catch the polarity of one next to it.
That's what that was
Yeah.
the question.
Right.
Yeah. How do you, yeah, what's the size?
Yep. And then the other part that limits how fast you can store something into magnetic medium has to do with inductance.
Yeah.
If you have not taken a class in electromagnetics, this is kind of outside of the scope of the class. But magnets are kind of like they're like flywheels, okay? Especially electromagnets. So when you have an electromagnet that is already having a particular polarity, it has a kind of momentum to it. You can't just say turn off and go the other direction, okay? So you would need it needs time in order to quote unquote spin down and then reverse the direction. And that also is a part of the limit of how fast you can read and write magnetic media. But all of those will be faster than a punch card, especially the writing of a punch card, which involves actual punching holes on a piece of paper. Punch cards are interesting because when you look at punch cards, they actually have a sequence number in it, which means if you have a big, huge stack of punch cards and you run to somebody and you drop all your punch cards, they're now out of order, there are specific devices to resort a stack back in order based on the sequential number on a punch card, which by itself is also represented as holes on the punch card. Okay?
So
Yep.
what's going to be faster than magnetism? Magnetism is already faster than
Light.
paper.
Okay.
Right, yeah.
So DVDs are based on the reflectance of certain frequencies of light. So they are faster because photonic devices are they respond a lot faster compared to magnetic devices. But we don't have the equivalence of a hard drive that's easily rewritable. I know we have rewritable DVDs and whatnot, but they are bulk rewritable and not individual bit rewritable. So are there any other related questions about how to store data offline, which is kind of off topic a little bit, but nonetheless it is still part of computer architecture. So no other questions? Okay. All right. So getting back to this part here is all the memory devices that we talk about in this class are all considered volatile. When you turn off the computer, they're all gone. Okay, when you turn on the computer, the reset will reset everything back to a known state, but it will have no idea of what the content was before the power on or before the previous power off. So are we good so far? Okay, all right. So at this point, I'm going to point out where you can get the processor that we'll be using for this class, because you might want to kind of download a version and just kind of look at it from time to time, even though we may not be getting onto the processor right away. So the way you get to it is go to the shared folder. And once you get to the shared folder, you go to processor. So there's one folder here called processor. And there are 3 files that you will need. You are going to need alu.circ, which is a Logisim file. You will also need processor 0003.circ, and there's one more which is registerbank.circ. So there are 3 files that you will need to download and open in Logisim in order to kind of look at the processor that we'll be using for the rest of this semester. Okay, so once you have selected those 3 files, you can right-click and say download. So what Google is going to do is to kind of zip it up first and then give you a zip file, then you can unzip it and put it onto your drive. So that's exactly what it's doing. All right, so they're all zipped up, and I am just going to save it to my temp folder. All right, and then I'll go to the temp folder to show you, what it looks like and how to open it. Oh, okay, that's not the right. I'm looking for one that is large enough. This one is good. There we go. All right, so I go to my temp folder and I make a new folder called processor. Go to that folder and then unzip. I think it's a Google, maybe it's just called processor.zip. There we go. And then from here, you open only one of the 3 files. So when you start up Logisim, processor 0003 is the one that you open. So I'll show you exactly how to do it. Okay, so we'll start up Logisim first. And then within Logisim, we go to that folder. So we go to /temp in this case. We look up processor. And inside processor, the folder, we have processor 0003, which is kind of the revision number of this processor. And then you click open, and this is the processor. Yeah, this is what we'll be using for the rest of this class. So it looks a little complex, but there are a few reasons why it looks more complex than it really is. The first one is we're looking at a smaller, screen. So that means things look a lot more busy than they really are. And then the second thing is it's just that there are a lot of wires going everywhere. Okay, so if you use Logisim to analyze this circuit, it has a lot of tools to help you to do that. When you're using the poking tool, which is already active, you can poke a wire and it will tell you where that wire goes. Okay, what that node connects to. So it's a great tool, because if you just want to figure out, okay, where does this connect to? What else does it connect to? Click on the wire using the poke tool, and it will highlight everything that connects to that particular node or net. Okay, depending on whether you're doing board layout or schematic capture, they're termed differently, but it's basically the same thing, the same electrical connection. Is that okay? All right. So next question, why do we talk about registers? Well, that's because the processor has a whole lot of registers in it. So I know you cannot really see the details, and it's okay. It's not the point of this discussion to show you all the details. So here's a register, here is a register, here is a register, here is a register. So we have at least that many registers on the outside. And then when you double click on this device here, or when you right click and say show register bank, then we have 4 more registers inside here. So yes, so registers are quite important as a construct inside a processor. Okay? All right? But besides registers, we also have other constructs that we have not talked about in this class yet. So that's kind of the purpose of today's class, is to go over all the other constructs that we need to understand in order to be able to read the processor schematic and understand how it gets things done. So I will name those things first. Here we have a multiplexer. Here we have a RAM device. Here we have a ROM device. And over here we have a demultiplexer. So those are the things that I need to talk about first before we know enough in order to understand how the processor itself works. So are we good? Okay? I'm just kind of giving you an outline of what we are doing at this point and how it relates to things that we'll be doing in the future. Yep.
Is register similar to cache, like on CPU?
No, it is not. It is volatile like cache. Okay, so from that perspective, it is kind of like cache. It is also a form of memory, which is also what cache is. But registers, the main difference between registers and cache is invisible to software. So no matter what you write, whether you write it in C or write it in Java or whether you write it in assembly, cache is for the most part invisible to you as a programmer. It is a hardware implementation to speed up something, but to you it is invisible. Registers, on the other hand, are visible, entirely controllable and addressable in assembly language programming. So they're really quite different in terms of concepts. One is what you really need to understand to program in assembly. The other one is just kind of like, well, it's a transparent hardware device to make things faster. But for the most part, you cannot control or even see it in software. So is that okay?
Yeah, no, that makes sense.
Okay. If you want to think about it this way, there's an analogy you can kind of use. The gas pedal is kind of like a register to a driver. Okay, you step on the gas pedal and the car goes faster, right? You let go of the gas pedal, the car should slow down unless it's on the downward slope, right? So by comparison, a turbo or turbocharger or a what is the other one? Compressor, huh? What is the other one? Supercharger. So a supercharger is more like a cache, where you really don't have direct control over the supercharger. Okay, you step on the gas, the supercharger gets compresses the intake air, but you don't really have any dial or anything to control the supercharger to say that no, I don't want 12 psi, I want 8 psi. Nope, you have no dial, no control. You might get a reading out of it, like it's running at how many psi, and that's all you can do. So cache is kind of like that. It's an optimization thing to help improve the performance, but as a driver, you have no control over it.
So it's physically on the die of a CPU, or you can't change it.
Correct. It may be on die, it may be off die. It depends on the integration, the level of integration of the processor. If you look at very old motherboards, back in the 486 or 386 days, cache is actually off chip. There's a separate bunch of chips to implement the cache, even level 1 cache, to those processors. But when you look at a modern processor, not only is level 1 cache on chip, level 2 and level 3 caches are also on chip. And that's because transistor sizes have shrunk significantly compared to the 386 days. So that's a good topic to actually look into, is how the size of transistors have transformed how much stuff we can pack onto a single chip. Okay. That reminds me a little bit earlier. I closed off a tab that talks about Moore's law, M-O-O-R-E, Moore. Does anyone know what is Moore's law? Okay, go ahead.
The size of transistors will double every year or every half.
It will shrink. It will shrink, or you can say the density, right? So the density of transistors will double every 18 months. Okay, so that's kind of a trajectory that this person Moore had projected, from a long, long time ago. So if you think about that, okay, so let's do some math here, and math is the domain of a spreadsheet. So we'll switch to a spreadsheet, which is all the way down here. There we go. So let's look at a processor in 1990. Okay, so in 1990, let's see. So in 1990, the 386SX processor was kind of popular. We were just transitioning from 286 to 386 at that time. Okay, so we have 1990, and then we have this year, which is 2019. So the question is, how many 18 months periods have passed, in these 29 years? So let's do some calculations. Okay, so we just say, let's take this year minus that year. Okay, that's the number of years. Okay, then you take the number of years, you multiply it by 12, and then you take the number of months, you divide it by 18. So we have experienced 19.333, basically 19 and 1/3 periods from 1990 to 2019. So the question is, if Moore's law holds true during the entire period of time, what is the change of transistor size over this period of time? If you think it is about 20 times, you'd be wrong. Because it is every 18 months doubling, right? So every 36 months is quadrupling, and then every, what is 3 times 18? 54 months, it is multiplying by 8, okay? And then 16, and then 32, and so on. So so the number that we're looking at is 2 to the power of 19 and a half, 19 and a third, not 19 and a third, or 2 times 19 and a third. So let's take a look at that number. So if Moore's law was holding true the entire time, this is the factor of change. Okay, a transistor back in a processor in 1990 is about 660,000 times the size of a transistor today in a processor. And you might think, well, does that make sense? Okay, well, let's do a little bit of fact check. Okay, so I'm getting you guys ready for election year because we'll have to do a lot of fact checks, right? All right, so we want to look into 386SX, and we are specifically looking into transistor size, okay? And I'm pretty sure we can find an answer to that. So let's see if this, nope. Oh, okay. That's not likely to have the answer of what I'm looking for. Okay, this might give me a little bit of an idea. Okay, so I'm just looking for transistor size. Nope, doesn't have that. Die size, this is the overall size, but it doesn't have, oh, it does have that. It has a process. So the 1.3 micron, 1.5 micron is basically the size of a transistor. What is a transistor today? What is the size of a transistor today? Well, we're down to nanometers now. So the question is, how many nanometers are we talking about? It's single digit now, right?
Yeah, I think it's 7 nanometers.
Okay. So let's take a look at 10th gen i7.
They're 12, I think.
They're 12?
AMD came out with 7 nanometer, I believe.
Okay. So we'll just take a look at one of these. Okay, it doesn't say anything about the process or the transistor size. So let's call it 10 nanometers. So how does 10 nanometer compare to 1.5 micron? So a micro is 10 to the power of -6, and then a nano is -9. So the factor of increase is not quite as dramatic as Moore's law predicted, but nonetheless, it is still pretty dramatic because we're looking at basically 1500 divided by 10, 150 times. So that's very conservative, it's just 150 times. Is that okay? But we are looking at just numbers. How does it, what really is a micron? I mean, how big is 10 nanometer, which is the size of a transistor? So to give you an idea of the scaling, okay, of all of this stuff here, let's look up the diameter of a strand of hair. Okay, and of course, this depends on the person. A human hair can range from 17 to 181 micron. which means even back in 1990, you can fit about 10 transistors across a strand of the cross section of a human hair, even back in those days. Okay, and we are talking about the finest hair of humans. Okay, today, because each transistor is only about 10 nanometers, you can fit 17,000 transistors across the finest human hair. If you just look at the cross section of a human hair, okay, and this is the finest one, which means it is the very soft, fine hair. You can fit 17,000 transistors across. That is the kind of scale we are talking about. Go ahead.
How can we make them so small?
That's
How do you even manufacture something like that?
It's magic.
literally.
It is all magic. Now they have a photographic process, so they have to use back in the older days, they use ultraviolet, light in order to etch and expose, to do the process. Now they're down to X-ray, which is an even higher frequency light, because the resolution they need is so high that even ultraviolet is too low as a frequency. It is too fuzzy for that process. So you can just look up semiconductor or chip manufacturing technology and look up on YouTube, and you will find tons and tons of tutorials and introductions of how it is. It is really quite amazing, how that process has changed over the years. Yep.
Heading towards stagnation, though, hasn't Moore's law
Yes.
ended?
Yes, so Moore's law is heading to a point where we can't really increase the density anymore, because the one thing that affords the increase of density of transistors has to do with we can make the insulation layer as thinner and thinner and thinner. Okay, because we're talking about the P and N transistors that we talk about, those are called field effect transistors. And one of the attributes of a field effect transistor is it needs an insulation layer, okay, between the substrate and also the gate. Okay, so there's an insulation layer between the substrate and the gate. That insulation layer is now getting down to multiple atoms thick, and it cannot be made any thinner, because if it were any thinner, then the quantum effect of an electron, around its orbital would give enough chances the electron can jump across the barrier to the other side, which would destroy the desirable property of a transistor. So if they cannot make the insulation layer any thinner, then they cannot make the transistors smaller anymore. So we might have hit a particular limit of making transistors smaller. But I would not be surprised that Intel or AMD will find a way to get around that problem and continue to increase the density of transistors. And why do I say that? It has to do with back in around 1990. So let me go back to the slide of 1990. Okay, so back in these days, when transistors were getting down to 1.5 thousand nanometers by today's standard, people already thought that they have hit the limit. Okay, my roommate, who was a double E graduate student at UC Davis, we play a name called NetTrek, NETTREK, which is inspired by Star Trek. We fly starships around and conquer planets. His call sign was submicron. A micron is 1 micrometer. Okay, it's just another word to describe a micrometer. So his call sign was submicron, which basically means impossible. And not only have we gone below a micron, it is now 100th of a micron. And as you said, AMD is now even smaller than 100th of a micron. So I would not be really surprised if they can continue to make transistors smaller, because as long as there's a motivation to do it, which is based on competition and profit, I would not be surprised that engineers will find a way to do it. Or they can stack, transistors in a certain way, which is already happening. Yep.
Cooling, though. Problem is cooling, like being able to keep the temperatures down or stacking.
Yep. So they would need either find a better way to get the heat out, or to reduce the heat the amount of heat. So they have to do one or the other. We may be hitting, this may be, you guys may live to see quantum computers becoming reality, because both IBM and Google now have created their own version of a quantum computer. So if they already have prototypes at this point, the amount of time to take something from research and prototype to production has shrunk, dramatically over the past few decades. If you think about, laser printers, okay, ask your parents or grandparents about laser printers, okay, and ask, how big and how much was a laser printer, when it first came out, and how much time it took to miniaturize and make it economical enough to sell at price. It took a lot of years, okay? And then you look at cell phones, okay? Ask your parents about the first cell phone, which looks like a brick, okay? It will literally slow down your Porsche because of the weight and how much power it consumes. Your alternator is going like, oh, I'm working really hard to charge that phone. Yep, but how long did it take until cell phones became super affordable and tiny and does not consume much power anymore? Not as long as laser printers, getting to become the price that they are at this point. Okay, look at LED or LCD TVs. Okay, flat panel televisions. How long did it take for a 60-inch television to go from what, $6,000 or something like that to the price point today? If you want to buy a 60-inch just 1080p resolution TV, how much is that nowadays?
$500, maybe less.
Exactly. From $6,000, how many years did it take to have that price shrunk to that point of $500? Not a whole lot. We're talking about probably less than a decade. So from that trajectory, I think the amount of time it takes to go from research, theoretical and research based quantum computers to production quantum computers is not going to be that long. Because technology feeds back into itself, right? Better computational technology will give you better ability to model stuff, and better ability to model stuff will help you discover stuff faster, and that just accelerates the whole cycle. Of course, when quantum computer becomes a reality, the one field in computer science that's going to be entirely upside down is going to be cryptography. Yep. Every single known cryptography that we use today is going to be out the window. It's going to be totally useless. So if you want to plan for your future, and make your future not as susceptible to quantum computing, studying quantum computers and cryptography and thinking about what happens when quantum computers become reality, that might be something interesting to look into. Yep.
I was going to ask earlier about quantum computers, but I brought it up. Do you know anything about how they store data? How they?
The only thing I know is it is probabilistic.
Yeah. Right.
It is not deterministic like computers that we have today.
Right.
So you have to observe something like many times in order to know what it is actually what the actual state is. But beyond that, I'm not really familiar with quantum computer.
Yeah, 'cause
Computer.
I saw last week or something that someone has a programming language for
Mm-hmm.
quantum computers now. It might be Microsoft, so I don't know if you know anything about that.
Nope, I do not know. Yeah, but the advance is going to accelerate. So we'll see faster and faster development in quantum computing. And quantum computing, once it becomes reality, it will propel all of the other technological fields, because it would just provide the massive processing power that we currently do not have to do simulation, AI, all kinds of intractable problems today will become like practical once we have quantum computing. So that's going to be one huge, gigantic, change in terms of the landscape of technology. That's one disruptive, one disruption that no other technology can compare to.
Right.
Yep. All right. Cool. So we are getting back to this picture, and then we say, well, of all of these things, what do we not understand yet? Okay. So we'll take a look at a multiplexer first. Okay. So I'm changing the order of the topics a little bit. So instead of just going sequential, which is RAM and then ROM and then multiplexers and whatnot, we'll start with a demultiplexer first. So when you want to look up the help file, it will give you all the information. So the first thing I want to show you is how to find reference material on these topics. So this is a multiplexer, okay, and I can make this window a little bit bigger. Okay, there we go. And it just describes what it is. So now the question is, well, I know how to get to this help in LogicSim, but what if I want to print this out so I can bring it to the next exam? Taking a screenshot of this is kind of tedious because it doesn't scroll very well. You can also copy and paste into Word or something like that, but there's a better way to do it. Okay, so I'm going to show you the better way to do it. Okay, so to illustrate the better way to do it, I'm just getting to the terminal that I was using. Nope, there we go. All right, so I want to use a different window to go to Documents, cisp310, and I want to see if LogicSim is already a folder. It is a folder already. So you go to download LogicSim, generic -2.7.1. But even if you do it in Windows, don't download the exe, download the JAR file. Because a JAR file stands for Java Archive, which means it is a zip file. It really is just a zip file. But Windows won't let you unzip a jar file because the extension is not ZIP. So how do you convince Windows to unzip a jar file? Change the extension. That's all it takes, okay? So change the extension of this file .jar to .zip, okay? Once you change the extension to ZIP, Windows will recognize it as a regular, normal zip file. Then you can unpack it, okay? Once you unpack it, this is what you will see, okay? I'm using the command line tool, but I think, can you see the blue stuff?
Yeah.
Okay. So it will give you all of these subfolders because LogicSim is not open source, it's actually open, it's public domain. So the source file is available here, we have resource, and we also have doc here. That's the documentation. So you change the directory to the doc subfolder, and what you see is something that looks like this. All right, so what do? You look at this and go like, what is DE, what is EL, EN, ES, PT, and RU? Those are languages, okay? RU is Russian. I think PT is Portuguese. ES is Spanish. EN is English. EL, I'm not sure. D is Deutsch, is German, okay? So take your pick, okay? I would just go for EN, okay? So when you look under EN, you have an XML file to talk about the actual content, and then you have something that looks super suspicious, HTML, okay? So you go like, HTML, sounds like something I can handle, right? So go to HTML and look at that folder, and it has got a file that is named index.html. That looks even more suspicious, right? It's like, isn't that normally what we go to when we go to a home page of something? You would be 100% correct. So what would be the next thing to do? I would be very tempted to just open that HTML file using Firefox, right? So you say Firefox index.html, and there we go. Welcome to LogicSim. Then you go to library reference. Wow, looks kind of like the stuff that we saw, except it's not on the side panel, right? So you go down to Plexer and you find Multiplexer. And here is the same content that we saw earlier in Logisim, except this time we are using Firefox to open it. So what is the difference? I mean, if I can see it in, in Logisim, why do I want to do this? Because you can Control P. Then you can print it out, okay? You can put it into a binder, right? You can highlight it. You can add your own annotation to it. You can do all sorts of stuff, once it is available as a regular HTML document, okay? So this is kind of my hint to say that, okay, for things that are important for this class, you might want to print it out, okay? So that you have a copy in your binder in the next exam, okay? You have all of this information, okay? If I ask you, okay, how do we use a multiplexer to blah, 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 you go like, I don't remember what a multiplexer is, but I have it on my binder, okay? I can just read it. So are we good so far? Okay. So since we have this page up, let's go ahead and check out what a multiplexer is. The behavior of a multiplexer is it copies an input on the west edge, which is this side, onto the output on the east edge, which is this little port here. Which of the input to copy is specified by the current value received through the input on the south edge, which is this little dot here, the pin that has a gray dot on top of it. I find it useful to think of a multiplexer as analogous to a railroad switch controlled by the select input. Yes? Oh, sure. Yeah, absolutely. Okay. I did not realize that it was out of the screen area. So let me just resize the whole thing to fit. There we go. But the idea is, it is just like a railroad switch, okay? Does everybody know what a railroad switch looks like? Okay, except in this case, it's a unidirectional railroad switch. Okay, you have multiple in, one out. Okay, it's directional. Is that okay? All right. So it now explains what each individual pin is, but the idea is, in this case, you have 4 in, 1 out, and then you have a 2-bit select here to say which one of the input becomes the output. Is that okay? Because if you have 4 inputs, okay, you can select 0, 1, 2, or 3 in order to select which one becomes the output. But how many bits do I need to specify 0, 1, 2, or 3? 2 bits. We only need 2 bits because 3 is 1, 1. So that's the idea of a switch, of a multiplexer. So a multiplexer is nothing more than saying, oh, we got 4 things that need to connect to this one thing over here, and I just need to specify which one of the 4 connects to the output. That's basically a multiplexer. Now, what about the other little pin here that is next to the gray dot? That is an enable. So you can make a multiplexer enabled, or you can make it so that it's always enabled. So if you have this pin here, it means you can say, just turn off the whole thing. Nobody gets out. Okay? Or you can have it enabled. Then it will take whatever input that is selected and use it as the output. Are we good with this? Yes? Okay. So once we know what a multiplexer is, what do you think a demultiplexer is? Reverse. Exactly. Even the picture looks exactly like the reverse of a multiplexer. So if a multiplexer is multiple in, 1 out, this one is 1 in, multiple out. But remember, it is a switch that is unidirectional, which means in this case, 1 in and multiple out, but not reversing the direction. But other than that, it's really just like a multiplexer. So are we good so far with the concept of a multiplexer versus a demultiplexer? It's a selection mechanism. Yep.
How would you choose if you had multiple to go out to different ones? Like, how do you like, is it an on? Like, if you have an on How do you choose which one to pick?
Okay, that's a good question. So basically, so let's say you have one in, and then you select 0, 1 as your out in this case. Okay, so what happens is the other ones are what we call not driven. Okay, so that means I need to first explain what is driven versus not driven. Okay, so that's a good topic to explore first. Okay. To explain that, let me see if I can use another device here to help us explain that. Controlled buffer is a good one. Okay, there we go. So what we want to do is to look into this. I'm going to magnify this a little bit because otherwise it's hard to read the text. So what we want to do is to first explain what is a control buffer. Let's forget about the inverter. We're not changing a 0 to a 1 or 1 into a 0. We are just copying, okay? Which has the symbol of something that looks like this. And then we'll just call we'll read the rest. Often called a 3-state buffer, each one has a 1-bit control input pin on the south side, which is this little pin here. The value at this control pin affects how the component behaves. Then it explains what it does. When the value of this pin is 1, then the component behaves just like a respective component, which is either known as a buffer or an inverter. In other words, if this pin here, the pin that is facing south, is a 1, it's kind of like a pass-through, okay? Except it's not a pass-through, it is re-amplifying the signal as it generate the output. So this is a typical mechanism that we use in order to say, oh, this signal needs to go to 64, other places, and there's not enough drive to do it. So, what a buffer would do is to amplify the signal. So you would go from one signal to fan out into like 8 of these, buffers, and then each one of the 8 buffers, each output of the 8 buffers will go to, 8 actual destinations. So you can now control the fan out and limit it to 1 to 8. Instead of 1 to 64, which may not be physically doable. Okay? It's kind of like, my voice is only so loud, okay? So let's just say that, over, in open space, when I speak, loudly, I can only get to 8 people, okay? But there are a lot more people like further down. What am I going to do? Each one of those 8 people becomes a repeater and re-amplify what I just said to another group of 8 people. Is that okay? So you can look at this like kind of like a megaphone. Okay, it re-amplifies a signal. So the control pin is basically the on-off switch of the megaphone. Okay, if you release the trigger on the megaphone, you can speak whatever you want into the megaphone, but nothing comes out of it. But when you hold the button down or when you pull the trigger and you speak into the megaphone, then whatever is the input becomes the output except quote unquote amplified. Is that okay? So now the question is, so let's say we have that scenario. We have a whole bunch of people, like 8 people out there. They're all listening to me. They're waiting for something, okay? And I don't speak. What are they going to receive? Nothing, right? Just background noise, okay? So that's what we call a non-driven state. So a driven state, on the other hand, is actively talking into the megaphone. So I can say 1, 0, 1, 1, okay? So the other side would now receive and go like, okay, 1, 0, 1, 1. But on the other hand, if I don't say anything, do they know whether I want to say 0 or 1? Nope. It's not, it's neither. Is that okay? So we'll go down this list here and go to the second item. So the second item is the one that is kind of tricky to understand. When the value is 0, okay, let's just say it's not unknown because unknown is not good. So let's just say it is 0. Then the component's output is what we call floating. Floating means it is just not driven. Okay? So are we okay with these concepts or not? Okay, sort of. I think we sort of get the idea, but sort of not get the idea. So let me give you a picture that might help illustrate the concept of driven versus not driven. So let me go to Zerno, make a new page, and let me draw this picture. Okay. So we have, power, which is a positive voltage. We have ground, which is a lower voltage. Okay. And we have two switches here. So we are not even talking about transistor. We are talking about actual switches. And this is where you attach your probe, to a multimeter. Okay. And I'll name these switches. This is switch 1, and this is switch 2. Okay. Now, obviously, if I close both switch 1 and switch 2, that is a bad situation because it's called a crowbar, which means, I am going to send a lot of current going from the positive source of voltage to the negative source of voltage, and something's going to burn. Okay, we just don't know what is going to burn, but something's going to burn. So we don't want to close both switches. But before if I close switch 1, then whatever you're measuring here is called driven high because it is electrically connected through the switch to a high voltage source. Is that okay? So driven high is just saying that, okay, I have a path through a switch or a bunch of transistors to a source of higher voltage. That's driven high. Then I open switch 1 and say, okay, let's disconnect it. And I say, let's connect or close switch 2. So if switch 2 is closed, then I have an electrical path from the point that I'm testing to the ground voltage, which is what we also know as the negative voltage. So in that state, this point, the point that you're measuring, is called driven low. We good with that? Yes? Okay. So now we open the switch again. So we have both switch 1 and switch 2 open at this point. And you measure, at this point here. What do you think you'll be measuring? Has anyone tried that with a circuit, with a multimeter? No one has tried this? Okay. The number is going to go all over the place because there's nothing driving it. It is quote unquote floating. So if it is floating, then shouldn't it just be reading 0 or a particular number? No, because this is a conductor. So if you have a conductor, what does it become when when it is not attached to a particular source of voltage? It becomes an antenna. And what do antennas do? They pick up all kinds of radio signals, right? So, and do we have all kinds of radio signals, like even right now in this classroom? The fluorescent lights, emit a lot of, electromagnetic, interference signals. Your cell phones do, your Fitbit also do that. So we have all the computers that we have, they all emit electromagnetic waves. So all of those electromagnetic waves would induce current onto this wire. And as a result, this point here, your test point, is going to experience changes, very slight changes of voltages, but it will be like constantly flipping around. Okay, that's called the floating state of a circuit. So are we okay now understanding what the word floating means in an electrical circuit? Okay, now is it a bad state? Not necessarily. If this point here is not being interpreted, it's okay to let it float. Okay, it doesn't really matter. On the other hand, if this point here is actually connected to something and something is actively trying to interpret what is this a 0 or 1, then floating is not a good idea. Because it can pick up a 1 at one point, pick up a 0 at another point. You have no idea what it is going to pick up. Is that okay? All right? So given this explanation, and we get back to the explanation of what a buffer is. So when this pin, which is the control pin, is a 0, then we are disconnecting the input from the output, and the output becomes floating. Is that okay? Which basically means this device is not telling what the output should be. It's just not care. Is that okay? So I think later on we'll, okay, let me see. We got enough time. So let me just go through one more circuit to explain why that is important. I'm going to create a new circuit here. And I'll do something, okay, let me magnify it first. And I'll do something that's pretty dumb, okay? I'll make a very dumb mistake here. And just connect two input pins together. Do we see a problem? No, this is not a problem because the top input pin is driving the wire low, okay? It's being driven low. The lower pin is also driving the wire low. So it's okay. It's almost like, you have a, let me see. It's kind of like having a spring-loaded, platform. And, one person says, I want this platform to go low. And then the other person says, yep, I also want it to go low. So you have two people trying to drive the same platform low. Okay, not a problem, because each person has enough strength to push the platform low already. Having two people to try to push it low is not a problem. Okay. What does become a problem is when one person says, I want to drive it low, and the other person says, I want to drive it high. Then we have a problem, because now all the strength of the first person trying to drive the platform low, the other person is trying to lift the platform up, and now they're fighting. Okay? In fact, this is also called a bus fight. It's a technical term. Bus fight is a technical term. So what happens here is you can see it's colored red because Latch system doesn't know who's going to win. So all I can say is like, I have no idea what's going on here. Something bad is going to happen. I have no idea who is going to win. Okay? That's why the Y is red. But what if I flip the upper one also to a 1? Then we don't have a problem anymore because both are trying to drive the line high, right? But one person is already enough to drive the line high. Having two to try to drive the line high is like, okay, duplicate effort, but whatever, right? So that's not a problem. Are we good with this little circuit here? Okay. So I'm going to change the circuit a little bit to basically say, maybe we should not be doing this, okay? Because if the two input pins can be different, they really should not be connected together because you can end up with a short, which is not a good idea. So what I would do instead is I will go to gates, get me a buffer, okay, and stash one over here and stash another one down here. Okay, and with each one, I want the output to be enabled. So I don't see the enable pin. Oh, control buffer. Okay, that's somewhere else. Let me get rid of these two because control buffer has its own little symbol. So that's fine. Okay. So now I have a switch to basically say, should I let this input through or not? Okay. So now the question is, what do we do about the output of these two control buffers? Well, guess what? I'm going to connect these two together. Okay. And we'll even call this node some kind of output. Okay. And you look at this and go like, tac, we still have an error state. Well, that's because the control of each one is still unknown at this point. Okay. I need something to say, okay, who gets to go through? Is it the top pin or is it the lower pin? So what I need is now a third input pin to say to go through. Is that okay? So we'll go ahead and make a third pin. The third pin is what we call a select pin. Okay, so I'll use SEL here, and might as well call this one, input 0, and we'll call this one input 1. This is basically what is happening inside a demultiplexer. Okay, so inside the demultiplexer, it's kind of the same kind of circuit, but not exactly the same. So I'm going to use the select pin here and connect it unnegated to 1. But I don't want to connect it I do not want to connect it unnegated to the other one, because otherwise both will turn on at the same time and both will turn off at the same time, which kind of defeats the whole purpose of the circuit. So what I would do instead is to negate it first before I feed it to the other one. So now I go get a NOT gate, and let's see, to make it look nicer, I can make it point north like that and move it here, and then connect this to the same select pin. So now I actually get to say who gets to connect through the device, right? So even if I change the input now so that one is 1, the other one is 0, they won't be fighting anymore, because we have a person directing traffic. It's like, okay, who should be able to get through? According to this particular select pin, input 0 gets to go through. Okay, what about input 1? Input 1 is not driving this wire anymore. This wire is only driven by the top buffer, but it's not driven by the bottom buffer anymore. Does it make sense? Is that okay? Okay. So we'll just go ahead and change the select pin and see if we can make input 1 to connect through the whole device. And this is what happens. Because when select is a 1, then in 1 gets to drive the buffer, which becomes the output. But because select is also negated before it becomes the control of the buffer connected to in 0, it is now a 0 as far as the buffer of in 0 is concerned, which means the buffer is saying, I'm not driving the output. I'll just let the output be whatever, right? I'm not going to force anything onto that wire. Is that okay? Does everybody understand what is driving high, driving low, and floating? Floating simply means I'm not putting any effort into changing the state of that output. Okay? Somebody else can do it. Is that okay? All right. Very good. So now we can finally get back to, oops, you cannot backtrack all the way because I changed that. So we can get back to demultiplexer here. So the question that somebody asked originally was, well, we don't have a problem with the input coming in from the west side. We don't have a problem with the selecting which one of the output the input would connect to. The question was, what happens to the other connections, right? So the answer to that question is all of the other connections, all the connections of the output other than the selected output will be floating. They are simply not doing a single thing. They're not going to specify what the output pin should be. Yep.
So I know 1 determines the amount of voltage, and that's what turns it on. So if you have a floating number which is reacting to what you said, getting voltage, will that ever cross the threshold of becoming 1?
Yes, it does. Unfortunately, it does.
And Logic, do you have to take that account or no?
No. In Logic Sim, okay, so a good design should never rely on a floating signal to do any type of computation.
Right.
Yep. So, so even though the input of something can be floating or the output of something can be floating, when it is floating, okay, so there are several scenarios. If a whole bunch of these things connect to the same wire, then the idea is only up to one of those will be driving, and then the rest will be not driving, would consider floating.
Okay.
Okay?
Those things are connected to something, so they could possibly trigger. Correct.
Correct. So you have to make sure that does not happen.
Okay.
Yep.
But not in Logic.
It's part of the design that you have to make sure that that does not happen. Yep. So are there any questions about the topics that we have just Yes, go ahead.
So you are basically just passing the input to one of 4 locations?
Correct.
Okay.
Yep. And in the process, you're also re-amplifying the signal. But
Right.
in our processor design, we never really need to re-amplify a signal. So we're really just saying, okay, this is the input. Where do you want to go?
Right. Yeah. Okay.
Yep. Mm-hmm.
Because then for a multiplexer, it's the opposite.
Right.
You have different inputs.
Yep.
So you have different numbers that you're putting in. So you have 4 different choices basically, and you just choose one of them. But here you have one choice and then just 4 locations for it to go to.
4 possible locations for it to go to,
Yeah.
and then whatever location it goes to, it will mimic the input.
Yes.
The other 3 would be floating.
Right.
So it would not try to drive the other 3 outputs. Those driving those, or it just doesn't care.
Right.
Yep. So we're doing okay so far with these 2 concepts. What a multiplexer is. You have one multiple in, one out, and a demultiplexer, which is you have one in and multiple out.
But it's only the one that comes out.
Right.
Yeah. That.
Yeah. So in this case, the analogy of a train rail track switch is good and bad. It's good from the sense of the train will only go onto one of the tracks, and then the other output of the switch will have no train coming out of the switch. So it's kind of like that too.
Yeah, because it's only one train that can pass through, but
Yep.
in a multiplexer, it's 4 trains that come in. And
Right. So in that case, you have 4 trains parked
Yes.
at the input, and then only one train gets to go through the switch, other side of the switch. Right. So are we still doing okay with these concepts? Okay. We are almost running out of time, but I do want to show what we'll be talking about next Monday. So next Monday, we'll be talking about the 2 memory devices that we need to use inside the processor. Well, one is inside, one is outside, but we're going to talk about RAM. Okay, this is what a RAM module looks like. And the other one is a ROM, which is this one. That's what a ROM module looks like. So we'll be talking about the ports of a RAM module and the ports of a ROM module. And then we'll talk about, okay, what happens if I want to read a location in RAM? This is what you do. What do we do when we try to write or overwrite a location in RAM? This is the sequence of operation. Okay, ROM is a lot easier because it's read-only, so it can only do one thing, but not quite the other. So that's going to be the focus of next Monday's discussion, at least the first part of the lecture, because I don't think it would take too long to explain these 2 items. And then after that, we'll start to look into the whole processor thing and start to say, how do we add numbers? How do we get 2 numbers to the adder? And then how do we store the result back into one of the registers? So we'll start to get into a routing of information and data inside the processor next Monday. So are we good so far? All right. There are no new lab activity for today. Okay. On Monday, on the other hand, we'll start to get used to the TTP toolchain, which includes a lot of interesting tools. I totally abused the Google spreadsheet program and turned it into an assembler. So that's going to be our tool to use to assemble programs.